This is SpaceTime Series 24, Episode 1. Coming up on SpaceTime, the most distant galaxy ever seen, new research on the origin of the Moon's magnetic crust, and Rocket Lab recovers its first stage booster following launch, an achievement seen as a first step towards reusable rockets. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have set a new record for observing the most distant galaxy ever seen. The ancient galaxy named GNZ11 is located some 13.4 billion light-years away. That's 134 nonillion kilometres, or to put that another way, 134 followed by 30 zeros. A report in the journal Nature Astronomy suggests that being so distant, and consequently so old, means this galaxy just about defines the very boundary of the observable universe itself. It'll help astronomers shed new light on a period of cosmological history when the universe was only a few 100 million years old. The study's lead author, Professor Nobunari Kashikawa from the University of Tokyo, says the detection will help astronomers searching for answers to questions like how big the universe is and how and when the first galaxies formed. Kashikawa and colleagues determined the distance to this galaxy by measuring its redshift. Redshift refers to the way light is stretched out, becoming redder the further it travels due to the physical expansion of the universe since the Big Bang 13.82 billion years ago. Scientists look for chemical signatures called emission lines imprinted in the spectra of light from distant objects. By measuring how far these signatures have moved to the red end of the spectrum compared to where they should be, astronomers can determine how far the light must have travelled, thus providing clues about the distance of the target galaxy. The authors specifically looked at ultraviolet light, as that's the area of the electromagnetic spectrum where they'd expect to find the redshifted chemical signatures. Kishikawa says, while the Hubble Space Telescope has detected spectral signatures in the light coming from GNZ11, it wasn't able to resolve the ultraviolet emission lines to the degree needed. So the authors turned to the more advanced ground-based Mossfire spectrograph attached to the giant 10-metre Keck 1 telescope upon Mauna Kea in Hawaii. Mossfire was able to capture the emission lines coming from GNZ11 in greater detail, thereby allowing the authors to make a far more precise estimation of its distance than what was previously possible. This is SpaceTime. Still to come, a new study looking at the origin of the Moon's magnetic crust, and Rocket Lab has successfully recovered one of its Electron first-stage boosters following launch, an achievement seen as a first step towards reusable rockets. All that and more still to come on SpaceTime. A new study has supported the idea that the Moon's remnant crustal magnetism was caused by an ancient molten iron lunar core generating a geomagnetic dynamo similar to that which still operates on Earth today. While the Moon no longer has an internal magnetic field like the Earth's, rock samples brought back by the Apollo missions show that it does have localized surface regions up to several hundred kilometers in size where very strong magnetic fields exist, raising questions about exactly how these fields could have formed. The findings, reported in the journal Science Advances, provides new insights into why the Moon's crust's magnetized, and it debunks the idea, an alternative theory, that it's the result of an amplification of the interplanetary magnetic field created by meteoroid impacts. That idea is based on observations showing large and strong magnetic spots on the other side of the Moon, which are exactly opposite large lunar craters. Because the Moon, unlike the Earth, has no atmosphere to protect it from meteorites and asteroids, such massive bodies can hit it with full force, pulverizing and ionizing material on its surface. A cloud of charged particles called plasma created by these impacts then flows around the Moon, compressing the magnetic solar wind present in space and thus strengthening its magnetic field. At the same time, the solar wind induces a magnetic field on the Moon itself. On the surface opposite the impact, all these fields are amplified, creating the observed magnetism in the crustal rock. At least that was the idea. However, one of this study's authors, Dr. Katrina Milchkovich from Curtin University, says the new research uses a deep numerical study to show that meteoroid impact plasmas interact much more deeply with the Moon compared to the magnetization levels obtained from the lunar crust. The results, therefore, suggest that a core dynamo process, such as that we see on Earth, is the only plausible source for the magnetization of the Moon's crust. The research looked at the large craters seen on the Moon caused by ancient meteoroid impacts. They're now filled with solidified volcanic basaltic maria, causing them to look darker than the rest of the surface. During the impact events which caused these maria, the meteoroids hit the Moon at very high speeds, causing displacement, melting and vaporization of the original lunar crust. The research calculated the mass and thermal energy of the vapor emitted during these impacts. That was then used as input for further calculations and investigation of the behavior of the ambient magnetic fields on the Moon following these large impact events. Milchkovich and colleagues developed numerical estimates for the vapor formation that occurred during the large meteoroid impact bombardments of the Moon approximately 4 billion years ago, a period known as the Late Heavy Bombardment. These were the first lunar impact and plasma simulations performed with enough computational power to realistically capture and test the meteor impact scenario. It gave the authors the opportunity to test a range of different impact scenarios, and in this way were able one by one to rule out this mechanism under any feasible conditions as a potential alternative source to a geodynamo to explain the Moon's remnant magnetic crust. So by ruling out this alternative, the findings further support the giant impact theory. That involves a Mars-sized planet called Theia colliding with the early proto-Earth some 4.5 billion years ago, causing both bodies to merge into a molten magma ocean, resulting in the creation of the Earth we know today, or at least as it would become today, with some of the ejecta accreting into orbit around the Earth and then solidifying to form the Moon. The findings also have implications for other bodies in the solar system with unexplainable magnetized crusts. As well as the Moon, Mercury and numerous asteroids and other small planetary bodies also have magnetic crusts which may well have resulted from a geodynamo.
We know that Moon's crust is magnetized from orbital measurements from missions that took a magnetometer on board, but also we know that from Apollo samples that Apollo missions brought back in the 60s and 70s. So we've measured the magnetization intensity in the lab as well. So the issue with the orbital measurements is that you always have to take into consideration kind of spatial resolution you get because you're orbiting high above ground level, but when you bring a sample back in the lab, you can really do justice. So we know from a few different investigations. Yeah, we know from different angles, we know that it is magnetized and roughly how much, yeah.
How did it get that way? There have been a few hypotheses as to how that occurred.
Yeah, I think the currently leading hypothesis is that Moon had a dynamo, that kind of its own dynamo that activated the magnetic field. So it had its own magnetic field thanks to a liquid core or outer core that would generate the magnetic field, like we have on the Earth, for example.
That would be justified when you look at how the Moon was formed, wouldn't it? Because there's a big blob of molten liquid orbiting the Earth following the giant impact, and that eventually coalesced to form the Moon. So a geodynamo sort of fits the bill.
It would fit the bill for sure, because all planetary bodies are big planetary bodies like moons and planets. They all form from this kind of conglomerates of gas and dust as you kind of go crunched together under gravity and under pressure. And by that, increasing the inner pressure actually would cause melting of the core. So then in that case, because all the heavy materials sink towards the core during the differentiation and formation of the Moon or a planet, then you get heavy metals going down to the center, but you also get high pressures in the center. So that's where you actually have a molten metallic materials that didn't feel any high pressures because of their center or planetary body. So that's kind of like the origin of magnetic field on planets in moons in general. But the hiccup with the Moon is that Moon is actually small compared to the Earth, for example. So as it evolved over time, it actually cooled down because smaller planetary bodies, they actually give away their heat much faster than big planets. Like Earth is cooling too. But it's a big planet, so it cools very, very slowly compared to the little Moon that actually cooled off very quickly. So because it cooled off, that could have caused some of that shutdown to happen. So it kind of like it's not as hot in the interior anymore, so it kind of starts to switch off the dynamo. So we don't really know actually.
We've seen the same thing with Mars, haven't we?
It could be a possibility too. Yeah, it could be a possibility as well. It's also a smallish planet compared to the Earth, but bigger than the Moon. So it might be the case. So like there would be kind of some logical thinking. You have a planet forming, it gets really hot, and over time it kind of, as it differentiates over time, it cools off, and then some consequences come with the cooling effect. The problem with the Moon is that it's not the fact whether it was ever hot or not, it's whether it ever had its own dynamo or not. Because the leading theory for crustal magnetization is to justify and to say, yes, it should have had, the only theory that's ongoing currently is that it had to have a dynamo back in the distant past. So when it formed, during the first billion years after it formed, it might have stayed in a dynamo before it got switched off. We don't really know why and how it switched off. We're kind of suspecting this might be the case. But also we're not sure that it ever existed. But the only real solid theory that at the moment hasn't been properly challenged, I mean, it has been challenged, but it hasn't been knocked down, is that it should have had its own dynamo in a distant past. And that explains crustal magnetization for other things.
The fact that it's differentiated means that it obviously was rotating at some stage. And with that rotation out being as slow as it is, just once every Earth month, approximately, in other words, it's tidally locked to the Earth, that also affects magnetism, doesn't it? The ability for a planet to maintain a magnetic field.
It may do, yes. When the Moon formed, it was much closer to the Earth. When it got tidally locked to the Earth, that's still an open question. Scientists believe it happened very early on in the lunar evolution, so when it was really close to the Earth. But then, just over time, the distance between Earth and Moon just got bigger and bigger. In fact, Moon is still moving away from the Earth at about
the rate of
that's a really good analogy. So it's like it does move away. Eventually, we'll lose it, right? This is still a bit of a conundrum, putting together all the dynamic of how the Moon looked like in a distant past, so close to the Earth. What was the state of the Earth also after big, giant impact? And then what's the state of the Moon soon after giant impact, and how everything started to cool off and form this kind of Earth-Moon system. So it's, I think it's a pretty fascinating topic, to be completely honest. And the only thing we have to go on are Apollo samples and remote sensing from spacecraft that we send around the Moon. And to be perfectly frank, I mean, Moon, in addition to Mars, has been really heavily studied. So we know a lot from the kind of exploration perspective compared to planets like Mercury, so only two missions.
But of course, this isn't the only hypothesis to try and explain the magnetic crust on the Moon. There's been another one involving lots of meteorite impacts. There's certainly evidence of that on the Moon too, isn't there?
Yeah, that's correct. So lunar dynamo, he's the leading theory for crustal magnetization on the Moon, but other scientists over time, they propose different theories as well and try to challenge the dynamo theory. The entire lunar discipline, lunar research discipline, completely exploded during the Apollo era because we all of a sudden started getting data and samples from that. So in the past few decades, there have been a lot of theories trying to explain what we see in the samples to start to begin with. So one of the theories was that big meteoroids or asteroids or comets that were hitting the Moon during the early evolution, like the first billion years or half a billion years after it had formed, would actually be so big and so energetic that the amount of vapor and plasma that comes out of when you see an explosion, there is a mushroom cloud, within that mushroom cloud, it would be so fierce and violent that it kind of pushes away the magnetic field, the ambient magnetic field, so kind of like the magnetic field that we sit in as a planet and the Moon, and that it would be able to bend them around the Moon as that vapor cloud, like that mushroom cloud, expands, that it would be able to bend over magnetic lines and focus them on the antipode of the Moon. And with that, by focusing magnetic lines, it actually increases intensity of magnetization in the crust, because the theory had to explain the actual amplitude of magnetization in the crust. It wasn't enough just to say, well, Moon is sitting in the ambient magnetic field, because the magnetization wouldn't be sufficient. But it kind of needs to show some way of amplifying magnetization in the crust. And so that was one of the theories that was proposed probably 2 to 3 decades ago. So you can imagine that a lot of that would come out of just drawing stuff on a paper and hypothesizing. Some of the modeling has been done, but it had included a lot of assumptions.
If you push those magnetic field lines right around the Moon and they reconnected, wouldn't that automatically increase the amplification of any magnetic field through magnetic reconnection?
Exactly, yes. So that would have been an original explanation or additional explanation why lunar crust is so magnetized, but it doesn't have a magnetic field, nor it can be magnetized by the ambient magnetic field. So like, where does it come from? So it had to come from some external source. Hey, impacts, they might kind of like affect the local magnetic field and then kind of focus them in specific areas in the crust, kind of like right at the back end of where impacts happen, and then kind of to justify the triplication of intensity that would generally be caused by the ambient field, something like that. So it was another theory that was kind of alive, as well as the dynamo theory. So we couldn't really be talking about the dynamo, and then sometimes somebody would say, how about impact? And it's kind of been like this ongoing competition between two theories. So we came together. This is a study that was led out of MIT in the US, and I got on board that project because I used to work with them there, and then I moved to Australia. So the project still kept going, but my expertise was in impact modeling. So what I do is model rocks from space, heating planets, moons, whatever, and create craters. So I actually have a shock physics code that would accurately simulate effects of impacts on planetary bodies. So that's already an advancement compared to like how this was presented previously. So I could calculate the mushroom cloud and the vapor cloud, the rate of expansion, the flux of gas and vapor and ionization that happens. So it's kind of like really physically properly quantify the effects of expanding vapor. And that got coupled with the lead author of the study, Rona Oren at MIT, who applied kind of the so-called MHD code, magnetohydrodynamics code, that really looks at like flow of that gas and ionization together with the magnetic field that's in the like ambient magnetic field. And then comes some fancy numerical math and physics to kind of check whether that expanding vapor can bend magnetic lines at the antipode. And the result of her calculation is whatever you throw at the moon in terms of like ambient magnetic field, as well as any impact that I throw at it, we can't reach the intensity of magnetization in the crust as it's been observed.
So the only option left is a Geodynamo.
Yeah, that's it.
Based on current budgets, there should be a human mission to the moon in 3 years' time, 2024, the Artemis 3. That must be exciting. And you must have your own ideas of what sort of rocks they should be picking up.
I am actually very humbled if in my lifetime I actually get to see a human walk on another planetary body. I wasn't, I was born after the Apollo era and haven't had a chance to kind of see that wonder, but I'm still at the complete awe that, this is finally happening again and that it's happening at another level. But in terms of science, it's just going to open a whole new chapter and a whole new avenue of possibilities for doing not only really cool research, because we'd be able to send scientific packages and get samples back if there is kind of active human travel between there and back.
They're building a space station between the Earth and the Moon.
Exactly.
Gateway,
so
this will become a regular thing. This isn't just a once-off.
I know, and then that's what
makes it be like Apollo
exciting.
17, where that's it. Well, no one's interested anymore. We're going home. The Moon will become the jumping-off place for human missions to Mars.
Exactly. And I think, and that's the bit that is kind of even more, I find it so unbelievable that I find it like it's so hard to believe that this is what's been planned and put in the budget. It probably is going to be pushed back. It's
always going to be pushed back.
But what I find amazing is that it's not only that we'd be able to physically send scientific packages and get more data and more samples there and back, like on a more active basis. It's the fact that the whole world and the commercial sector is now getting more and more involved with it. It's kind of like making sustainable human presence on the moon and beyond, but also engineering advances that need to be made to accommodate human presence and the scientific research presence and exploration presence. It's just going to explode exponentially. And that's what I'm so looking forward to see finally happening.
That's Dr. Katrina Milchkovich from Curtin University, and this is Space Time. I'm Stuart Gary. Still to come, Rocket Lab successfully recovers a booster following launch as a first step towards the eventual creation of reusable rockets. And Russia launches 36 OneWeb broadband internet telecommunications satellites into orbit. All that and more still to come on Space Time. Rocket Lab has launched a payload of 30 satellites into orbit and then capping off the mission by recovering its Electron first-stage booster, considered a first step towards developing a reusable rocket. The aptly named Return to Sender mission was the company's 16th from its launch complex on New Zealand's Mahia Peninsula and the 6th and penultimate launch for 2020.
The vehicle is fully on internal power.
Launch load is complete. System is in recirculation. Anti-gas ring disabled.
Stage 1 and Stage 2 tanks are pressed.
High flow engine purge is enabled. Deluge is activated.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2.
Stage 1 propulsion is nominal.
Entering Stage 1 burnout detect mode.
And we have liftoff of Electron from Rocket Lab's Launch Complex 1. We're just 50 seconds into flight, and you heard the call out on comms there that the mission is continuing nominally. So Electron will approach max Q along its trajectory, otherwise known as maximum aerodynamic pressure.
Approaching maximum dynamic pressure. Past maximum dynamic pressure.
And there goes the call from our operator on console. Electron has cleared max Q. Propulsion is continuing to look good on the path to orbit.
Stage 1 guidance is nominal.
Coming up next in the mission timeline is main engine cutoff, also known as MECO, as Electron's Rutherford engines power down so that the first and second stages of the vehicle can separate cleanly. Following that, the vacuum optimized engine on the second stage will ignite to carry the satellites on board further into space, while Electron's booster will begin to fall back to Earth, marking the start of our recovery attempt. The team on the recovery vessel will now be furiously checking its return telemetry.
MECO confirmed.
Staging.
Stage 2 ignition.
Recovery telemetry nominal.
Flight analyst, recovery LDN mission cord, execute sequence 53, Stage 1 recovery operations.
Computing landing zone.
MECO is confirmed, and so too is the startup of the second stage Rutherford engine. With the separation of Stage 1 and 2 complete, the trajectories are looking good so far while we're awaiting fairing separation. Fairing separation.
Stage 2 propulsion is nominal.
Electron's second stage burn is in progress as we hit 4 minutes and 17 seconds into flight.
Stage 1 apogee.
Just a quick update for you all here. Electron's second stage burn continues nominally at a velocity of 14,000 kilometers per hour and an altitude of 190 kilometers.
We're now at T plus 6 minutes and 8 seconds into flight, and both our second stage burn and first stage booster re-entry are looking stable. Next up will be battery hot swap to continue supplying power to the second stage engine and systems.
AFT is saved.
Stage 2 propulsion is nominal.
Stage 1 re-entry.
We've had battery hot swap confirmation, and we're about a minute and a half away from when we expect Stage 1's drogue chute to deploy. The ride is going to get a little bumpy on the way back down, with the booster reaching several times the speed of sound on its fall back to Earth. We should expect the first stage's main parachute to deploy at about 8 minutes and 44 seconds into the mission.
SECO confirmed.
Nominal transfer orbit. And as you just heard from the team in mission control, the engine on Electron's second stage has shut down and the kick stage has separated. In approximately 45 minutes or so, the payloads will be deployed to their precise locations using our innovative kick stage. Electron's second stage takes us to an elliptical orbit where the kick stage then separates. From here, the 3D printed Curie engine on Electron ignites to propel the stage and its payloads to a circular orbit for deployment. Using a cold gas reaction control system, or RCS, the kick stage accurately points itself to deploy each satellite to a precise and individual orbit, even on rideshare missions with multiple satellites like this one. Once the satellites are deployed, the Curie engine reignites, propelling the kick stage to a lower orbit, where it will be dragged into the Earth's atmosphere faster, leaving behind no space junk in orbit.
We've just had confirmation of successful drogue chute and main chute deploy.
The mission's payload of 30 small satellites were deployed into a 500-kilometre high sun-synchronous orbit an hour after launch. The flight also saw Rocket Lab successfully recover the 18-metre-tall Electron rocket's first-stage booster, which undertook a guided parachute splashdown into the South Pacific Ocean some 650 kilometres off the New Zealand east coast. A recovery vessel then retrieved the booster, which is now being analysed to determine the sorts of modifications that are going to be needed to make the first stage reusable. The Electrons are too small to undertake a powered landing, such as those used by SpaceX for their Falcon 9 rockets, so the company instead wants to slow down the boosters using a guided parachute descent and then snag them in midair by helicopter. They'll then be refurbished for reuse, a significant cost saving for the small New Zealand-based company. This is SpaceTime. Still to come, Russia successfully launches a payload of 36 OneWeb broadband internet telecommunications satellites into orbit. And later in the science report, Australia commences production of at least 50 million doses of the Oxford University AstraZeneca vaccine. All that and more still to come on SpaceTime. The Russian Federal Space Agency Roscosmos has successfully launched a payload of 36 OneWeb broadband internet telecommunications satellites into orbit. The mission aboard a Soyuz 21B rocket equipped with a frigate upper stage was the only launch undertaken in 2020 from Moscow's new Vysokochny Cosmodrome in Russia's Far East. The 36 150kg Ku-band satellites were deployed into a 450km high low Earth orbit about 5 hours after launch. The spacecraft will eventually move themselves into 1,200km high operational orbits. The launch had originally been planned for April last year, but was delayed after OneWeb collapsed and went into bankruptcy, forcing the British government and an Indian telecom to bail the company out. This latest launch brings to 110 the number of OneWeb satellites now in orbit. An initial 6 were launched from Kourou back in February 2019, followed by 34 more a year later in February 2020 from Baikonur, and then another 34 in March, also from Baikonur, before the company collapsed. OneWeb plans to have an initial constellation of 648 satellites in orbit over the next few years, with ultimate plans for a fleet of some 47,844 satellites. However, the US Federal Communications Commission, which has jurisdiction that the satellites were built in Florida, has so far only approved 1,280 satellites, with growing fears about what will happen to these satellites when they become redundant and the increasing problem of space junk. This is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with the Science Report. The first COVID-19 vaccinations have begun for 450 million Europeans as a more virulent strain of the coronavirus continues to spread around the world. The new, more transmissible mutation was first detected in England, has now spread across most of Europe as well as the United States and Australia. The only good news is it appears to be no more deadly than other variants of the virus, which has now killed close to 2 million people and infected at least 80 million others. The new strain is estimated to be some 56% more contagious than other COVID-19 strains. Meanwhile, Australia has started production of at least 50 million doses of the Oxford University AstraZeneca vaccine at the CSL plant in Melbourne. The Oxford adenovirus vector vaccine, which has just been approved by the UK, doesn't require the minus 80 degrees Celsius storage regime of the Pfizer messenger RNA vaccine. The Pfizer vaccine is on track to be approved in Australia by the end of the month, with at least 10 million doses on order, and the first delivery is expected in Australia by March. It's been rated at 95% effective, while the Oxford vaccine was shown to be 90% effective on 1.5 doses, but only 62% effective on 2 full doses. However, the company is now claiming 100% effectiveness against the most severe cases of COVID-19. A report in the journal Nature Communications claims scientists have developed a new method of drawing carbon dioxide out of the atmosphere and converting it into a useful fuel. Researchers at Oxford and Cambridge universities have created a cheap method for using iron, manganese and potassium to convert carbon dioxide from the atmosphere into a propellant, creating an overall carbon-neutral fuel. The study's authors said that this new CO2 conversion method's easier than previous ideas, making it a potential candidate for industrial use. Paleontologists have identified a new species of ancient crocodile from fossils dug up in southeastern Queensland. The prehistoric croc, named Paleodirex vincenti, is based on a giant fossilized skull dug up near Chinchilla in the 1980s. Now, in Latin, Paleodirex means swamp king, and Vincenti honours the late Jeff Vincent who made the discovery. Now, based on its 65-centimetre long skull, Swamp King would have measured more than 5 metres or 15 feet in length. Now, that's almost as big as today's estuarine or saltwater crocodile, Crocodylus perusus, also known as the Indo-Pacific crocodile, which can exceed 6.3 metres or 21 feet in length and weigh over 1.3 tonnes. But Swamp King had a broader, more heavily set skull, and so would have resembled a salty on steroids. Cracked or smashed smartphone display screens and their repair cost may soon be a thing of the past, with scientists developing a new cell phone screen that repairs itself. The self-healing material is a colourless electronic polymer developed by the Korean Institute of Science and Technology. It features glass-like transparency along with strong tensile strength and does not suffer scratches even after folding hundreds of thousands of times. The key involves using microcapsules of linseed oil with silicon and then coating them on colourless polyamides. The microcapsules break when damage occurs, causing the linseed oil and silicon to leak out and flow into the damaged areas where it hardens. In a world already filled with astrologers, tarot card readers, seance conductors, and failed TV cooks promoting magic COVID-19 cures to the gullible, comes more extreme religious propaganda pushing the dangerous practice of gay conversion therapy. The new push in a documentary called Censored claims God doesn't make LGBTIQ people, so a person's sexuality must be a choice, and that choice can be changed through religious counselling, spiritual growth, and, if necessary, aversion therapy. In reality, all the scientific evidence shows that gay conversion therapy doesn't change sexuality, but it is likely to cause its victims increased self-loathing, depression, and a greater likelihood of suicide. Tim Mindham from Australian Skeptic says the dangers are especially acute for adolescents who are still discovering their sexuality anyway.
So the conversion therapy is gay conversion therapy, which is basically a practice done by fairly fundamental religious groups or fairly sort of strict religious groups who consider that gayness is basically a choice done by people often under the influence of the devil or whatever, and that they can get gayness out of people through this conversion therapy, which is an interventionist type thing where you basically blast away at the poor teenager, as it often is, to sort of say that Satan, get out, blah, 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 or, get rid of this thing, become a good Christian and you'll be a better person, because naturally gayness is a heinous crime and is the work of the devil, and therefore no good Christian should be gay.
I wonder if the people making those claims are wearing clothes of different material or sowing different crops in the same field.
You being sarcastic there, Stuart? Yes, I know, exactly. Now, the whole thing is that because gayness is a horrible thing as far as these people are concerned. God could not have created it. So it must be some other reason. So it's either a trend or it's Satan. And the whole thing is that it does not work in any case. That's the whole thing, that you put someone who's often a teenager struggling with their identity, if you like, who is sort of, not sure where they are, suddenly hit with this pretty aggressive intervention in a religious setting where they've already come from. There's obviously people from a religious family, etc. You are traumatizing these people, or worse, sending them into areas that people shouldn't be sent into, almost, I presume, all the way to suicide. And yet this does not work. It's never been proven to work. You can't, by lambasting people with an argument, you don't ungay them. Some people might repress their feelings, but it doesn't mean they're not gay.
It's amazing how many of the people who are engaged in this sort of activity are actually closets themselves. There was a great case in Hungary recently of a politician who was very anti-gay in his actions, and he was caught at a gay bar.
Yes, or you might have politicians who espouse family values and then are carrying on an affair. Yeah. Seriously?
That's Tim Mindham from Australian Skeptics. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more space time, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.